G'day guys, and welcome to our lesson on power. We've already introduced the concept of work, which is the amount of energy you put into a system. And you measure work in joules. So work, joules. And it's equivalent to a force applied over a distance. So if someone said they walked up a mountain, here. If you knew the height of the mountain, and the weight of the person, and the gravitational constant, which here will approximate to 10, you could figure out how much energy it took for them to go to the base of that mountain to the top of the mountain, and therefore how much work they did. However, if you didn't know how long it took them to get to the top there, then you don't really know how much power they exerted to go up. If they took a long time to climb that mountain, like this, well, they're not moving very fast, perhaps they're overweight, perhaps they're sick, they have some kind of knee injury. They're not exerting a lot of power to get up to the top. However, if they rocket to the top like this, you think, wow, they must have had very powerful legs to make that trip in such a short time. So when we talk about power, we're talking about the amount of work you can do per unit time. And the formula reflects that. Power is equal to work over time, or we could say the rate of the work you're doing. And the unit for power is watts. Watts given by the symbol W. Don't confuse the work here, the W for work, with the W for watts. Watts is a unit of measurement and work is an actual concept. Okay, so let's see how power can be measured. Say we have a block of mass 10 kilograms sitting on the ground. And then it's lifted up here to a height of 3 meters. So 10 kilograms. This would be the 0 meter height, and this would be the 3 meter height. Since the base has moved 3 meters up, we know the center of mass of the block has also moved 3 meters up. And this occurred over a time of 2 seconds. First of all, let's figure out the change in gravitational potential energy. I'll put work is also equal to delta E over delta T. Whoops, no, just delta E, yeah. So let's figure out delta gravitational potential and also the power. So first of all, the change in gravitational potential. Gravitational potential here is equal to, well, the formula is UG equals mgh. So gravitational potential here equals 10 times 10 times 0. 0 joules. The gravitational potential here is equal to, so I'll say that's UG0, and this is UG at 2 seconds, is equal to 10 times 10 times 3, or 300 joules. So this block over here has 300 joules more energy than this block over here in terms of potential energy. So the change in gravitational potential energy is equal to 300 take 0, or 300 joules. So to get the box from here to here, the work must have been 300 joules, somewhere in between here, in between these two periods of time. So if power is equal to work on time, the power of whatever lifted the box, say it was some kind of machinery with a rope pulling, to get it from here to here is equal to work over time. That's 300 over, it happened in 2 seconds, the lift, and the power was 150, that's joules per second, and joules per second is watts, 150 watts to get the box from here to here. Now, if I change something about this question, if I say it didn't take 2 seconds, it took twice that long, 4 seconds. That means power equals work over time, that's 300 over 4, and it's not 150 watts this time, it's 75 watts, so it's become less powerful. Just like our mountain analogy. If the person takes a long time to reach the top, we said their legs weren't very powerful. And that's because power equals work over time, and as time becomes big, power becomes small because we're dividing by a larger term. However, if they really rocket to the top like that, time becomes small, and therefore power becomes large. Dividing by a smaller term equals a bigger result. Let's look at another type of question where we have, this time, a truck traveling at a constant speed, and we're going to figure out the power of its engine. So we'll say here, the velocity of the truck is 20 meters per second. The frictional force acting that way is equal to 5,000 newtons, and the acceleration is equal to 0. It also has, well, it must have, some kind of driving force of the engine. So there's two parts to this question. First, we'll figure out the driving force, and then we'll figure out the power of the engine. So we know if acceleration is 0, the sum of forces has to be 0. Therefore, the driving force has to equal the frictional force there. So Fd is equal to 5,000. If Fd were larger than 5,000, there'd be acceleration in that direction. And if Fd were smaller than 5,000, the friction force would be larger than the driving force. The truck would slow down like that. So Fd is equal to 5,000. Now power is a little more difficult. We're going to solve it first of all the long way and then show the short formula for solving. So in 1 second, this truck moves 20 meters. It's moving 20 meters per second. So the work done in 1 second is equal to the force of the engine multiplied by the distance. This is the work done by the engine. The net work done on this truck is 0 because friction is also doing work. But if we're trying to calculate the power of the engine here, so engine, we're looking only at the work done by the engine, not the friction. So the work done by the engine is force times distance. Distance was 20 meters in a single second. So that would be 5,000 times 20, 100,000 joules. And since power is equal to work over time, we're already looking at the 1 second. You know, it's moved 20 meters in 1 second. Therefore, power is equal to work over time. That's 100,000 divided by 1, which is equal to also 100,000 watts. That is the power of the engine. Here is the alternative formula. If you don't want to put this time up and say, assume we're looking at a time frame of 1 second, you can say the power is equal to the force multiplied by the velocity. So here, the power is equal to the force of the engine, 5,000 newtons, multiplied by the velocity, which is 20 meters per second. 5,000 by 20 is equal to 100,000 watts, so meters per second. That also tells us here that watts is Newton meters per second. Newton meters is equal to joules, and if you divide joules by seconds, you get watts, as we saw before. So in terms of an object moving at a constant velocity, if the frictional force is equal to the driving force, that is when it's moving at a constant velocity, acceleration is 0. You can find the power of that driving force by multiplying F by V. Let's look at a more complex version of this question, this time with a slant. So we have a 30-degree slant here. We have a box sitting on the slant. It weighs 10 kilograms. Well, actually, it's not a box. We'll say it's an electric car. And it's moving at a constant velocity down that slant there. And that velocity, as of right now, is a mystery. So a few more knowns. Number one, the power of the engine, power engine, is equal to 1,000 watts. And there is a frictional force acting up the plane there of 250 newtons. And the other force here is the driving force. Let's figure out the velocity this electric car has to be travelling at in order to maintain a constant acceleration. So first of all, we put in the weight force there. So the four real forces acting on this box are the frictional force, the driving force, the weight force, and the normal force. We don't really have to worry about the normal force because that cancels out with this component of the gravity force. So we're really just looking at gravity, driving, and resistance. The gravity force here is 100 newtons, and we can actually resolve that into two forces, one here which cancels out the normal force, and another one here which will force the box to travel down this direction. It'll apply a force to the box parallel to the plane, which is equal to sine 30 times 100, or 50 newtons. So there is, if we resolve the forces, there is this imaginary force travelling parallel to the plane of 50 newtons. So if you can see, I'll just circle the key parts of this diagram now. 250 newtons acting that way up the plane, the driving force acting this way down the plane, and 50 newtons acting that way down the plane. If the box is not accelerating in that direction there, if it's a constant velocity, then the sum of the forces parallel to the plane have to be 0. So the sum of forces equals 0. Therefore, FD, the driving force, plus 50, those are the ones acting down the plane, have to equal the forces acting up the plane, 250. So we can solve for the driving force there. If the driving force was smaller than 200, the box would slow down because of the friction force acting that way. And if the driving force were larger than 200, we'd see some acceleration down the plane there. That's the driving force. The next part we want to solve is what is the velocity of that motor? Well, we know the power of the engine is 1000 watts, and power equals force times velocity. If power equals 1000 watts and force we found equals 200, then we can also find the velocity that this car has to be moving at so it does not accelerate. 1000 divided by 200 is equal to 5 meters per second. So to summarize this little lesson again, power is related to work. Work tells you how much energy was put into a system, and if you bring time in, you can then tell the rate of the energy put into a system. The unit for energy is joules, the unit for time is seconds. Power has a unit watts, which is equivalent to joules per second. If an object is raised out of the Earth's gravitational, or up in the, vertically in the Earth's gravitational field, the gravitational potential energy has changed, and that is equal to the work you put into the object. If you know the time, you can calculate the power of that lift. Furthermore, if you have an object moving at a constant velocity with frictional force, you can figure out the power of the driving force using P equals F times the velocity, the force times the velocity. And you can apply that same type of rule to an object moving down a slant. Power pops up again in electronics and photonics because the current moving through a wire also does work. As you know, if you ever turn on a light bulb or driven a remote controlled car around, and that work is being done at a particular rate, which gives us the power there. Look to the electricity lessons to see power pop up again.